Hello, my name is Adrian Mroczek, and this will be my final presentation for my computer technology project at Curtin University, Collision Detection for the Blind. Background and objective. The white cane is used by the blind and vision impaired as a mobility aid. It is by far the most economical and efficient method employed to aid users to move about independently. However, it has several drawbacks. For example, canes make no allowance for overhangs, such as branches hanging over walkways, and is poor at detecting drop-offs, like stairs leading down. It also doesn't warn the user of upcoming obstacles. These drawbacks can lead to severe injuries from incidents such as falling onto train tracks or walking face first into a low-hanging sign. My goal for this project is to solve this problem and increase the safety of the blind and vision impaired by bundling readily available and affordable technologies, implementing them to create a device that is integral to the cane, compact and unobtrusive to the user. About the blind and vision impaired. Everyone is aware that the blind rely on white canes to move around and sense the environment. They also rely heavily on their hearing to maneuver and detect upcoming obstacles. For this reason, I had to make sure that the collision detection feedback provided to the user doesn't impede on their hearing. During my research for the project, I learned that there is a lot of training involved to operate the white cane. The two main techniques for operating a white cane is the constant contact and touch technique. They both require the user to sway the stick side to side across their body in an arcing pattern. But one technique requires constant contact sliding across the floor, and the other taps side to side a small distance above the ground. Due to the long usage over various distances traveled while using the white cane, some users experience fatigue in the wrist. This made me constantly re-evaluate my device's weight, trying to reduce it where possible. About the solution. After researching various technologies usable for collision and object detection such as radar and infrared, I opted to use the pulse-based LiDAR method. LiDAR stands for Light Detection and Ranging. This technology works on the principle of radar, but uses pulses of light from a laser to measure distances from a target. The pulse laser beam is transmitted and reflected from objects such as trees, vegetation, buildings, people, and cars. Once the pulses return, they are recorded and the distance between the sensor and the object is calculated using the time-of-flight principle. LiDAR was chosen over other methods because it has a longer range and larger field of view, helping detect curved obstacles and bounce of angles. It is better suited for indoor and outdoor applications, working well in the sunlight without the need for recalibration due to filters and optics, while taking readings extremely fast. The time-of-flight principle is a method of measuring the distance between a sensor and an object, based on the time difference between the emission of a signal and its return to the sensor after being reflected by an object. To utilize this method, I chose to use LiDAR Lite version 3 sensor being produced by Garmin. Interfacing with this device is done by using an Arduino Nano acting as a master. The gyrometer and accelerometer from the MPU 9250 inertial measuring unit is used, calculating the swing angle as the user operates the cane. The LiDAR sensor and the MPU are communicating over the I2C protocol on the Arduino's I2C bus using different addresses. Feedback of impeding collisions is given by using a LilyPad vibe motor. All these devices are communicating with the microcontroller using the Arduino wiring language. The majority of the code is written with the help of readily available libraries from manufacturers and the Arduino community. Some devices require to be coded manually while referring to their respective datasheet and register map. To dictate whether there is an impeding overhead collision or a steep drop-off, I created a function that calculates the change in distance as a percentage, while using the current and previous distance. Then if statements use this percentage change and the angle of the servo to activate the LilyPad vibe motor, warning the user of the collision. The type of collision is distinguished by the type of vibrations given. One long and two short vibrations means that there is an overhanging collision, while 3 long vibrations mean that there is a drop ahead. By the end of the project, my initial expectation of hardware and components required increased dramatically. It required the use of additional components such as capacitors, voltage regulators, LiPo batteries acting in parallel, and more resistors. My original design also changed from using a Texas Instrumental MSP430 microcontroller to the Arduino Nano V3 for better form factor and lighter weight. Here is a visual representation of my schematic using fritzing. Both sides of the board are used to create the circuit. As you can see, the IMU is being powered by the 3.3 volt pin from the Arduino Nano. Its SDA and SCL lines are also being connected using 2 resistors, which are 4.7 kilo ohms. The LiDAR light sensor is also being connected to the SDA and SCL pins from the Arduino Nano directly using the onboard pull-up resistors. The battery pack is also being connected to the board through the voltage regulator, regulating the voltage to 5 volts throughout the board. Final hardware list. As briefly explained earlier, my initial expectation of the hardware required for my project increased drastically during the course of the project. For my prototype, I am using the Arduino Nano V3 as a microcontroller, the LiDAR Lite version 3 by Garmin as the sensor to measure the distance between objects, the Spark Fun MPU 9250 inertial measuring unit using the gyro and accelerometer. Further, my vertical motion, which is used to rotate the LiDAR Lite V3 up and down 0 to 180 degrees, I'm using the GWS Servo Mini STD. To provide feedback to the user, I'm using the LilyPad Vibe motor. I'm also using 2 pull-up resistors at 4.7 kilo ohms for the SDA and SCL lines on the inertial measuring unit as specified by the datasheet. I also need to use 2 capacitors, one for the LiDAR and also one for the power source, just before the power goes into the circuit, as specified by the LiDAR datasheet. I'm also using 2 LiPo 3.7 volt 900 milliampere per hour batteries running in parallel, giving me a total of 7.4 volts and 1800 milliamperes per hour. Due to the power source being greater than 5 volts, even with a 1.5 volt voltage drop, I was required to use a voltage regulator to regulate the voltage going through the circuit to 5 volts. Prototyping stages and challenges. During my initial prototyping, I had to calculate the overall current draw of all components and voltage required for the circuit using their respective datasheets. During stage 1, I coded each individual component and made sure that they worked properly independently. And during stage 2, I slowly bundled each device onto the breadboard one by one and tested the coding. In stage 3, once all devices had been added to the breadboard, I ran them simultaneously with serial output to debug the programming. In stage 4, I modified the code as needed and added any additional functionality. In stage 5, the design and printing of the case was done using the 3D printer provided by university to hold the device and components in place. In stage 6, I fixed the breadboard inside the case that was printed, connected and seated all the components, and mounted them as necessary, and began testing the device for final stages. During my initial prototyping, the biggest challenge I faced was experiencing voltage drops. After realizing that I didn't have enough power going through my circuit to power all the devices, I used a multimeter to measure the voltage going through the circuit. I quickly found that while using my 5 volt battery source, I was experiencing a voltage drop of 1.5 volts. To overcome this issue, I went out and purchased a 6-cell battery caddy and attached 5 1.5 volt batteries, giving me a total of 7.5 volts, and with the voltage drop it circulated 6 volts throughout the circuit, giving me enough power and current to power all the devices on the circuit. Using the 6-cell battery caddy also presented another challenge. I found that using 5 1.5 volt batteries increased the weight of the whole entire device dramatically. So to resolve this issue, I switched to two 3.7 volt LiPos running in parallel, which was significantly lighter. I also quickly learned that using a voltage regulator is unsafe. This is because voltage regulators get extremely hot over a short amount of time. This is a big risk to the user and also to wires and other devices connected to the breadboard. So for future implementations, I aim to do a design or modify my design without the use of a voltage regulator, and I think using 2 LiPo batteries will be sufficient without running in parallel will be sufficient without using a voltage regulator to power the circuit. The reason why I chose to remove the voltage regulator is because I experienced a short circuit as I accidentally touched the VCC line from the external power source onto the voltage regulator, which heated the cable, damaging the cable, and also landed on other cables, destroying them and some pins on the breadboard. Here I'll briefly explain more about the code. I explained the code in more detail in previous presentation videos, and it will also be documented heavily in my final report. But starting from the top, you can see that I used the wire, lidar light, and servo libraries, create an object for those devices, set the pins, create some variables to store the data, and begin interfacing with the device, activating the device within the setup method. My main void loop calls the servo function, which operates a servo using an if statement, changing the angle and position of the servo during every loop of the code. And then while it's within that method, it'll also make a call to the measure distance function, which uses the lidar light and takes readings, distance readings, and compares them with variables within the feedback method, and if certain conditions are met within the if statements, it will warn the user of the different type of collision that they may face up ahead. In this section, I will briefly go over the code used for the inertial measuring unit. It is quite long and extensive, so I've only included 2 main snippets, which are the function of the complementary filter and the calibration of the IMU. So in the complementary filter function, I begin transmission on the register used by the inertial measuring unit, which is 68. I then begin to start writing to the register 3B, which is XL X out H, and end the transmission. I then begin requesting 14 registers from the device register and begin reading from those registers as well. I then convert the timer's output to seconds from microseconds and start the timer again so we can calculate the next delta time. I then calculate the orientation of the accelerometer relative to the Earth and convert the output to degrees. The data is used to correct any cumulative errors in the orientation of the gyro. Then I convert the raw data of the angular velocity to degrees per second. The value 131 is used because, referring to the data sheet, it refers to the sensitivity scale factor used by the IMU. We then applied a complementary filter which calculates the angle based on integrating the angular velocity to an angular displacement. The filter then adds a small correcting factor from the accelerometer roll or pitch, so the gyro knows which way is down. Then the calibrate MPU method is used to set the registers, set the initial reading of certain registers used by the accelerometer on the X, Y, and Z axis, the temperature, and the gyro on the X, Y, and Z axis. And then I assign default values. I set up default values for the roll and pitch, and also the gyro X angle, gyro Y angle, the complementary angle of X and Y, which is later used in the calculations to calculate the complementary angle. This is required initially to calibrate the MPU with default variables, and we also start the timer at the end, which is used for other calculations. So here I'll briefly go over some output and results as seen from the serial monitor while running my code and debugging and testing the devices are working. So first I will point you over to COM15, where you can see readings of the current distance and previous distance and the percentage change between those distances as it's being read. I also keep track of the current angle of the servo because I use those values within the if statement to meet, and if certain conditions are met, it will alert the user based on those conditions, dictating if it's an overhang or a steep drop collision. So as you can see in the example, the previous distance is 170 centimeters, and then the current read distance is 14 centimeters, which indicates a percentage change of negative 97% at a current angle of 158 centimeters. So within the if statement, I set up the conditions that if the percentage change is greater than negative 40, it means that the object is, or at an angle of, I think it was 140 to 180. It means that an object is close to the head, and it'll warn the user of a impeding collision. In the output shown from COM16, here you can see the readings from the IMU. Those initial readings during the initial debugging and setup of the IMU are just the raw data values from the gyro and the accelerometer. This was done before I before I applied the complementary filter. Later on, after I did apply the complementary filter, I did get the desired results and accurate angles as seen in the COM3 picture below, but unfortunately I didn't record that data output, and as explained earlier, I had some issues with my circuit which damaged my IMU and did some short circuiting on the board, which means I can't go back currently to get the output and present it. So as a brief example, I've used someone else's output, which is pretty much exactly the same as I was getting from my IMU. Because of these issues with short circuiting due to the external power source touching the voltage regulator and damaging some pins and devices, I wasn't able to do a live presentation or a final presentation of my project, but thankfully in previous videos during the prototyping stages I did demo what the overall project would look like as it's operating. So you'll see that in the next slide as an example. In this slide I am presenting my prototype in its 3D printed case. So I have mounted the LiDAR light sensor to a bracket which connects to the servo motor, which is then mounted onto the 3D printed case. Within the case I have fixed the breadboard and circuit with all the components attached. I have also mounted the IMU on a little ledge within the 3D printed case. I have also cut a small hole large enough to fit a USB through to power the Arduino Nano over USB and also upload code as needed, rather than having to remove the breadboard and prototype out of the board constantly, which is a bit of a nightmare. I've also realized that there's more than enough room, and in later renditions I might also decrease the size of the actual case itself. Summary and conclusion. What has been achieved? Over the course of my project, after all the research, prototyping and implementation, I've created a prototype where the overall cost of the device is a lot cheaper than other devices on the market that detect collisions and obstacles. For example, the Ultra Cane, which uses narrow beam technology, costs approximately $1,087. The total cost of my device with all the components is approximately $300 bought off the shelf. I have successfully implemented a sensor to measure distance at a high speed and high accuracy while rotating vertically as the cane moves horizontally, which then warns the users of collisions from overhangs and drops when certain conditions are met. I have also achieved my goal of creating a 3D printed case to house all my components and circuitry, while also remaining form factor and lightweight, reducing risk fatigue for the user. Firstly, I would also like to thank Professor Ian Murray, who has provided me with a lot of helpful advice during the course of my project, led me in the right direction to solve problems I encountered, and provided me with a 3D printer used to prototype the case. Secondly, I'd like to give some recognition to Kern University for helping fund my project by purchasing various components used in my prototype, most notably the LiDAR light sensor, which was the most expensive. In this slide, I'll do a brief reflection about my project. So what still needs to be done for the project moving forward? As I continue with the project, I aim to find and implement better ways of recognizing collisions and obstacles using data output from the sensors. This will improve the performance and provide better safety for the end user. Further down the track, I plan to investigate ways to control the maximum measurable distance. It will be good to reduce the range to approximately 5 meters. This will reduce the amount of unnecessary environmental obstructions that could lead to false positive detections. Earlier in the project, I investigated and implemented a method to reduce the range by increasing the speed at which readings are made, but this also reduces the accuracy of the scans. I will also attempt to reduce the overall complexity of the prototype by changing the LiDAR sensors communication protocol to pulse width modulation. This will resolve any issues of register addresses clashing on the I2C protocol. The problem of gyro drift also needs to be addressed. This provides inaccurate results because the output will drift slightly over time. I have tried solving this issue by applying a complementary filter to the output. This seems to have removed the gyro drift, but further testing will need to be done for a definitive answer. Unfortunately, this might require the purchase of another IMU. The component doesn't seem to be functioning after the short circuit discussed earlier before capturing results. The problem faced trying to get the angle from the stick in motion using the IMU still needs to be addressed. Tracking the angle can be used to provide more accurate collision and obstacle detection. How could the project be improved? Or how could I have improved the project? If I dedicated more time to the project and had better time management, I would have fixed a lot of the underlying issues and bugs with the prototype without needing to rush. This would have given me the time to optimize the code and prototype before the due date. Ideally, I wanted to present the end product that was soldered to a printed circuit board, making the device more compact and lighter. So what did I learn over the course of the project? The biggest knowledge gained was how to properly read and make use of data sheets and register maps. I learned how to code, manipulate, and activate the IMU and LiDAR registers using functions from the inbuilt wiring library for the Arduino. Thank you for listening to my presentation. Here is a list of references used throughout my project. This is just a small sample, but these references apply to some things discussed in today's presentation.